So welcome everybody to today's edition on our webinar on emerging topics in biomolecular magnetic resonance. We have two fantastic presentations today, and both speakers agreed to recording. So we are recording, and we will upload the lectures to the ICMRBS YouTube channel. Please use the Q&A box and not the chat box to place your questions, and feel free to put the questions already during the talk. If you raise your hand, we can also unmute you and you can directly talk to the speaker. And please be reminded about the early career researcher webinar of the ICMRBS, which is very active. And there's one more announcement for today. So because next week there's Euromar, and as Lyndon Emsley said, Euromar is like Christmas for NMR spectroscopists. So we will make a break next week and resume in 2 weeks. With that, I would like to hand over to Michael Glöcker, Stefan Glöcker, which will introduce the first speaker.
Yeah, thank you very much, Marcus, for the brief introduction. And today I'm very excited to introduce Henrik Ardenkjær-Larsen. Just a few words to him. So he studied and obtained his PhD from the Technical University of Denmark. He then continued to work there as a research scientist before he then joined Emersham, which later became part of GE Healthcare. Since 2015, he is professor and section head at the Technical University of Denmark as well. And very notably, Jan-Henrik has received several awards like the Günther Laukin Prize and the Gold Medal of the World Molecular Imaging Society. Yeah, he's renowned for his work for signal enhancement and especially for developing the dissolution DNP technique, which, yes, a technique that is actually currently on the way into the clinics. And yeah, if you allow me to add a few personal words. So I was about at the end of my PhD thesis when this amazing work came out with dissolution DNP that showed that you can actually observe biochemical reactions in vivo in clinical studies in humans. And that got me very excited and has very much inspired my own career pathway. This may actually be what convinced me to why I'm doing many things that I'm doing today. And this is why I'm especially excited to hear what you have been up to recently, Jan-Henrik. So Jan-Henrik, this floor is yours.
Okay, well, thank you, Stefan, for this very, very kind introduction. And I know you're doing amazing work yourself in this space, so yes, I understand that I have about 20 minutes, so I've been trying to limit myself to a smaller topic that is of particular interest to me, and so I'm not going to talk so much about the, let's say, the clinical translation of the hyperpolarization and dissolution DNP. Let's say the biological and medical applications of that. But I would like to talk about something which is, well, has a lot of my interest with, which is hyperpolarized water. So trying to hyperpolarize protons, also for medical applications. In my case, there are other uses of that and other interests in that. And a combination with UV radicals, which also has some interesting, say, properties and broader use than what I am going to talk specifically about today, and I'll try to sort of point that out when I get to that part. Well, firstly, thank you very much for the invitation to speak today, and then I'd like to disclose that I am still an employee of GE Healthcare, so I have an affiliation with them, and I'm also the owner of Polarize that manufactures instrumentation for hyperpolarization. Right, so dissolution DNP, I'm sure that most of you are familiar with the method, so I'll just spend a minute on that, just to explain the principles of it. And the idea is that we take our sample with our imaging agent, our molecules of interest, formulated in some matrix amorphous sample, And then we dope into that sample electron spins, free radical. The electron spin has a high magnetic moment, so we can more easily polarize the electron spin. We put the sample in a magnetic field, and then we cool the sample down to a few Kelvin, which is sufficient to fully polarize the electron spins. And then we irradiate with microwaves close to the resonance frequency of the electron spin. The electron spin will then polarize the nuclear spins in its vicinity. That nuclear polarization diffuses into the bulk by spin diffusion, and we end up with a solid sample which have nuclear spins that are highly polarized under the conditions that we work at, and with radicals that have good properties. We can get tens of percent of polarization on the nuclear spins, and even higher. Then we make a fast phase transition from the solid state to the liquid state, a large temperature jump from 1 Kelvin to room temperature by simply dissolving the sample, injecting a hot solvent on the solid sample, and we end up with a liquid solution of the molecules of the nuclear spins with the nuclear polarization almost fully preserved. The spins, the nuclear spins, do not notice this phase transition, this temperature jump, and then we can detect a strongly enhanced liquid state signal in our NMR spectrometer, here illustrated by urea. Very high signal to noise in a single scan, same sample over the weekend in our 9.4 Tesla NMR spectrometer generates a signal that is very weak, so 10,000-fold enhancement of the nuclear polarization, and that is exactly what we need in order to use this liquid sample, hyperpolarized sample, as a contrast agent in vivo. We have to overcome the concentration reduction that, as we go from highly concentrated water that we normally image to millimolar concentration of metabolites. We like to use this method for study of biological systems, study of metabolism of small organic molecules that typically go into the energy metabolism, that are fast taken up and converted by cellular systems. And one of our interest is to use that in cellular systems. So this is an illustration of my lab. We have several NMRs. This is one of the most used setups, 500 megahertz NMR with a cryoprobe, DCH cryoprobe. This is pretty optimal for hyperpolarized work. We have good dispersion of this field strength, and the T1s, the nuclear labeling positions that we normally look at, still have long T1 before we get CSA relaxation kicking in. So this is a pretty good field strength, and with a DCH cryoprobe we can do proton deuterium decoupling, and we get really good, excellent NMR sensitivity in this setup. We couple that with our polarizer, so that is very close by, and then we have a transfer system that allows us to inject directly into the NMR tube very fast. In, let's say, 1 to 2 seconds, we can acquire an NMR spectrum. Then what we're currently working on is to combine that with an NMR bioreactor, so that we have also a circulating medium to keep the cells viable in the NMR tube. They are confined to the active region of the NMR probe, and then we keep them viable by perfusing the medium, and then we can inject hyperpolarized substrates sort of at intervals, and to interrogate the cellular metabolism and perturb these cells in various ways. So this is where we're heading, and we're not quite there yet, but this is a typical application of dissolution DNP. Also for medical application, which has been the main driver, and where let's say it was part of the original motivation for entering this field and developing various hyperpolarization methods. This is also what from my lab, actually, it's we're currently in the process of setting this up, but this is very typical from also the way we work at hospitals, that we have our MR scanner, which could be a clinical 3 Tesla MR scanner with multinuclear capability, because we need the MR scanner to be enabled for X nuclei, not just protons. We then need, again, the polarizer in close vicinity in an adjacent room. We can quickly transfer the sample to the scan room and inject into the animal or the person, and that's typically a manual transfer of a syringe that is then connected to a power injector, and it's injected into the patient. We work a lot on the technology. We need to develop the receiver technology, so array coils, like you see it here, optimized for carbon-13. We need to reduce the electronic noise because now we work at a much lower frequency, 4 times less for carbon than protons, and the electronic noise of these small receive elements are important. And we would actually like to exploit these receive arrays for accelerating the MR acquisition. And then we also need to develop pulse sequences that are optimized for the fast metabolic conversion and that are efficient in terms of encoding these 3 spatial dimensions and the spectral and temporal dimensions with good temporal resolution as well. So that's very demanding on the pulse sequence as well. So here you see an example of 3D sequence of stacked flip stack spirals, as we call them. So the individual slices in space. Now, the polarizers have also evolved over time. The original polarizer design was used also in the first clinical study. We took that into a clean room to do the first study at UCSF. And then we developed in parallel the Spin Lab, which was an automated version of that, and got rid of the clean room installation by bringing that into the, let's say, inside the polarizer and keeping the sample sterile and safe to inject. Yes, and then Oxford Instruments introduced the Hypersense, which was a preclinical polarizer based on the same original design. But that was unfortunately discontinued 5-6 years ago, so there's been no access for the community to hyperpolarization equipment. And that has recently been, let's say, rectified by the introduction of the spin aligner from Polarize, which is a startup company from my university. So now there's a preclinical polarizer which is commercially available. So this is how the polarizer technology has developed in our hands. There's been alternative designs from other academic groups. So this is just, let's say, my track of polarizer development. Now I just want to illustrate okay, sorry, this will not run this video. Okay, anyway, I will quickly skip this because many of you have probably seen it, but this is the most exciting illustration of the dissolution DNP experiment. This is a video from Oxford University that I often use because it shows a very manual procedure of hyperpolarizing a DNP sample. What you would have seen in the video, apologize for that, it doesn't run. Is that the sample has been sitting in the liquid helium for about an hour to be polarized by DNP, and the 2 PhD students are now ready for dissolving the sample. So they would heat the solvent and put the stick in, inject manually the hot solvent, and retrieve the sample in this syringe that you see on the slide from this receiver that collects the hyperpolarized solution, and then quickly run to the scanner and inject it into the tail vein of a rat in this case. This is the more recent polarizers that I showed on the previous slide. The same experiment becomes a little boring because now there's no running and no steaming and no very rapid manual procedures because it's all been automated. Now to the subject of today, hyperpolarized water. This is the idea here is that with the hyperpolarization, we're able to create a very strong polarization. With protons, we have a very high diamagnetic ratio, and we can also keep or achieve a relatively high concentration. So we can potentially obtain a very large magnetization, which is orders of magnitude larger than what we normally have in our MR scanner, the water proton magnetization that we have in the scanner. So we could have a very strong signal source for depicting anatomy and getting higher spatial and temporal resolution of the anatomy. So that's the idea. And with MRI, we eliminate the ionizing radiation compared to CT, and we could also get away from gadolinium-based contrast agents if we could just hyperpolarize the water protons. Our aim is angiography, coronary angiography, which is still a challenge in MR, and also perfusion, because water would be a freely diffusible tracer compared to gadolinium, for instance. So that would really give you better abilities for quantifying perfusion of the tissue. There's all been other applications that are studied by other groups, and I'll just give you a couple of examples. Well, firstly, the Sanjay Hans group has been looking into using the Overhouse effect for polarizing the water, and this has the advantage that this is a continuous method that generates the hyperpolarized water. And but the Overhouse effect is only effective at low magnetic fields. So the magnetization that can be obtained in this way is inferior to what we can do with dissolution DNP. And then there's been some work from EPFL and from Lucia Friedman's group on using the also hyperpolarized water in studying proton exchange, water exchange in protein systems. Now with water, or with protons, the limitation is a short T1. So water has a T1 of bulk water is only 3.3 seconds when degassed. Then we can increase the T1 by increasing the temperature, or we can dilute the protons in a deuterated matrix. And in that way, we can actually get a pretty long T1 for water protons. The challenge is that we need the free radical in the DNP process, and the radical will then, after the dissolution, be a dominant relaxation mechanism. You see here that even when we have diluted in T2O, the 1 minute T1 that we could have would be reduced to 10 seconds in the presence of the radical from the dissolution DNP method. Others have suggested ways of getting rid of that. Lucio's group tried to use extraction of the radical into an organic phase to get the radical out of the aqueous phase. The EPFL group suggested the quenching of the radical chemically with ascorbic acid, which requires a lot of ascorbate and which is a relatively slow method. So both of these two methods have some limitations. Firstly, we need the organic phase, and you need a lot of ascorbic acid in the other. So we use that in some of our first work that I'll show at the end of the talk. But now we would like to use the UV radicals because they have these special properties that you can turn the electron spin on and off. As I say, they are labile, and you can generate the radicals, and then you can quickly or easily quench them in a solid state and get rid of that paramagnetic relaxation. This was inspired by work that came out also from EPFL a few years ago, where I think they, by more or less coincidence or as a side effect of some other work with light, discovered that one of the most used substrates, pyruvic acid, was photolabile and generated free radicals. So you see here the EPR spectrum from pyruvic acid when it's been irradiated with UV light. This paramagnetic center works for DNP, so you can turn the microwaves on and generate polarization. Not very good in this initial work. You turn the microwaves off, it goes back to thermal equilibrium, and that's so DNP. And then if you just blow some hot gas, heat the sample briefly, then you can actually quench these radicals, and then the EPR spectrum goes away and the solid state T1 becomes very long. This is something that we also are very interested in terms of generating solid samples which have very long T1 that would allow us to transport them, take the solid sample out of the polarizer and transport them over longer distances before we do the dissolution. So that's a primary aim. But here, in the case of hyperpolarized water, the idea is that as we do the dissolution, the radicals naturally goes away because they're not stable. Now the pyruvic acid, the radical, the nature of that is shown here in various forms of pyruvate to understand the couplings and the spectral. With then labeling in different position, carbon 13 can give some hyperfine couplings that allow us to understand where the electron spin is located. That means that we can actually shape the EPR spectrum by introducing or removing hyperfine couplings. But the bottom line is that the analysis leads us to know that this is the type of radical that is generated, that the electron spin is localized strongly to the C2 carbon. And this is the stable form that we generate after the UV radiation. Now the radical quenches and the quenching temperature is around 200 Kelvin. So that's what I mean by heating the sample briefly. It's still cold, so it's still a solid sample. But this temperature, increasing the temperature to about a couple of hundred Kelvin and then cooling it down again allows us to get rid of the sample. And that, in this case of this radical, the decomposition are very benign side of products. It would be CO2 and acetate. So they're very benign from a biological point as well. So that's quite nice. The EPR spectrum of pyruvic acid is good for DNP, as you saw in the previous slide in the initial work, but doesn't really give the very high polarization that we normally get with tridal radicals, which have an EPR spectrum which is more optimal for low gamma nuclei like carbon-13. So you can see here compared to the tridal EPR line, it's the UV radical on pyruvic acid is broader, and that reduces the efficiency of the DNP process. It's not quite as broad as nitroxides, so it's somewhere in between, and that means it's not good for protons, it's not good for carbon. We can manipulate this spectrum as I alluded to before. So by removing hyperfine couplings, either putting methyls instead of the or removing the proton on the methyl by methylating that C3, then we can reduce the hyperfine couplings and get a more narrow spectrum, and we can further deuterate that and get an even more narrow spectrum. That would be good for carbon polarization, low gamma nuclei. In the case of protons, we actually need a wider spectrum. So here you see the spectrum of a nitroxide, and in the blue the pyruvic acid. But we need to broaden that a little bit because it doesn't really cover the Lambda frequency of the proton, and we can do that by introducing a hyperfine coupling, a carbon-13 splitting. So if we do C2 pyruvate instead of normal pyruvate or C1 pyruvate, then we get a spectrum which is actually quite optimal for protons. And then we can transfer the sample into our polarizer. And this typical sample is like we have water, we need some glycerol to get the amorphous sample, and then we put some pyruvic acid in as a precursor of the UV radicals. So and then start the microwaves to polarize them. And here you see the efficiency of the DNP. So this is a typical water glycerol sample with some tempo, and it polarizes very well. Nitroxides are good for proton polarization because of their spectral width. We can get 80% polarization with about a 5-minute time constant.
And Henrik, when you play the movie, turn off the sound because we cannot hear you when you talk while the movie is also making sound.
Sure, I will. With pyruvic acid, then we get a slower DNP because of the narrow line of the pyruvic acid. So you can see this is slower and it polarizes not as good as the pyruvic acid. That's because pyruvic acid generated an EPR line which is too narrow. So now we introduce a C2 coupling, and then we can get a line width of the radical, which is perfect for proton polarization, and then we get a polarization which is similar to the nitroxide, and also a time constant of 6 minutes. And then we can actually further get the higher polarization and faster buildup if we dilute the protons, and we get fewer reduced number of protons in the sample that has to be polarized by DNP. And you can see here that we can get really, really high polarizations with a very fast time constant of 3 minutes. So very efficient DNP under these conditions. And then we just need to dissolve it and transfer it. We heat the solvent, inject it quickly on the sample, and then transfer it to our NMR spectrometer. In the case of nitroxides, or if we have paramagnetics in the sample, then we need a magnetic field not to have relaxation in liquid state. In the case of UV radicals where they're quenched, it's not critical and it's not essential. but magnetic tunnels have been developed and used quite a lot in dissolution DNP work because then to avoid the low field relaxation. But actually, if the paramagnetic species is quenched, then there is no low field relaxation and it's easy to transfer. And you see here the end result of the dissolution. We can actually preserve the polarization. If we have the paramagnetics present, the temple, then you can see there's a big loss in the dissolution because of the presence of that. And the T1 is very short. If we have UV radicals, then they are quenched in the dissolution, and then we preserve most of the polarization, and we can get 50 to 70% polarization in the solid state after dissolution, and long T1, so 30 to 40 seconds, which is pretty good for protons and good for this application. And here you see some examples of imaging with that. You can see that we can actually get a magnetization, which is several hundredfold above the thermal polarization in the MR scanner, the 3 Tesla scanner. When the hyperpolarized signal sample decays to thermal equilibrium, it's much weaker. It's into the noise, 20 times less than the 110 molar proton water sample. That's because it's diluted in deuterium, and the product of these two numbers would then be the enhancement that we generate from the DNP 4,000 times approximately. But really a very, very strong magnetization initially that allows us to do very good anatomical imaging. And here you see an example of pig heart where the catheter has been placed in the coronary artery, and then we inject the hyperpolarized water directly in the arteries. And you see here very nice angiograms and distal vessels in the myocardium. This is just free breathing, no special optimized cardiac imaging, but very nice angiograms anyway. And actually you can see that the myocardium is starting to light up. So also very nice perfusion of the myocardium is depicted. And this is something that we would like to, the next step for us with the 10 times better polarization that we have now with the UV radicals than what we had at the time where we still had the 5% polarization done with the ascorbic acid quenching of the radical. Normally coronary or perfusion imaging is done with arterial spin labeling or with PET, and this is really what we are trying to match with the hyperpolarized water. So I hope I've convinced you that we can actually polarize protons with dissolution DNP, and we can get a very strong magnetization, that the concentration T1 product can have various optimums, and we have some flexibility on that. And we can actually achieve a very long T1 with protons, at least sufficiently long that we can do imaging and we can inject it into a pig or eventually a patient. The challenge is that the T1 is quickly reduced as the water is mixed with blood. It will drop quickly to the 1 second as it gets mixed with the blood and diluted. So we have to do an intraarterial injection at the moment, but one of the projects we have currently is that we try to encapsulate that and protect the protons to do intravenous injections. But we have already very, very good quality images with even the lower polarization that we had a couple of years ago. And water is actually a very interesting tracer for diffusion quantification because it's freely diffusible and much more biological, natural than many of the diffusion agents that we use in MRI and CT. So thank you for your attention and acknowledgement of my collaborators and my group. And
yeah, thanks, Jan, for the exciting talk. So everyone, please feel free to put your questions into the Q&A dialogue that I can then read out. And if you really like a question, you can also give it a like and promote it to the top. Yeah, while that happens, I've probably a question for you, Jan, that you may get a lot. So if you actually do the dissolution in D2O, how biocompatible is D2O actually? I mean, is there possibilities to inject it into humans at some point, or does one really have to come up with different strategies?
No, I actually think it's the toxicology is I mean, favorable, but of course we have to do formal toxicology. This is a bolus injection, and it's a lot of deuterium. But I think it's actually, even though deuterium is not I don't recall the abundance, but if you calculate how much deuterium we have in the body, we have significant amounts. And I think this is very comparable. And And we are giving deuterium already as contrast agent. So deuterium labeled glucose is used in various challenge tests. So we are already, there's already clinical evidence for loading people with high amounts of deuterium. This is the bolus injection of D2O, so there would have to be done, of course, some toxicology, and I cannot say for sure how safe it would be, but I'm quite optimistic that it's doable.
And maybe I missed that. How long can you trace water if you inject it in vivo? So once you have it in the body?
Yeah, it was a little fast, but the T1 is long relatively long, like 30 seconds in the syringe. But as we inject it into the blood and it mixes with the blood, it drops to the 1.5 second that is a T1 of blood at imaging field strength. But it is a very tight bolus, so that would take like 5, 10, 15 seconds before that happens. It's not enough to give to allow intravenous injection, so we have to inject at the spot where we want to image, like in the video you saw the intraarterial injection. But you could see that it actually perfused the myocardium very well, and we were able to see full perfusion. So I think it is sufficient to do perfusion quantification as I speculate. We have to demonstrate that, of course.
Okay. We have a question.
How big was the bolus? I mean, how much?
It's about the bolus is about I think in this case 10-15 ml.
For the pig.
In a pig, yes. Yes. So like a 40 kilogram pig. So I think in a patient, it would be like, for instance, if we take like pyruvate and the clinical studies that we're doing at the moment, we inject something like 0.5 milliliter per kilogram, so 40 milliliters in a patient. That's a very typical contrast agent dose, and that's a volume which is fairly insignificant. Much of the preclinical work is done with higher volumes, higher concentrations, non-clinical conditions, but that's typical clinical conditions.
Yeah, okay, thank you. So I have two questions from Thomas Schmidt and Jeffrey Bodenhausen that deal with the actually pyruvic acid radical, which is basically how much is the conversion of pyruvate to its radical UV exposure dependent, and how pure does the pyruvic acid need to be for good radical yields?
Well, purity has not been something we have been too concerned about. So we have that seems to work pretty well with the purity that you buy from suppliers. The generation of the radical is something that we have optimized quite a lot. So the wavelength of the UV source is quite important. Power is also important. You saw how we made the beads. So the light, the UV light is absorbed. So the penetration is important. So you cannot have too large beads or a bulk sample. So that's the reason we prepared the sample like that. But the conversion is fairly efficient. We can generate concentrations of radicals which are optimal, which are comparable to what we dope with stable radicals like tridral or tempo. So 40 to 80 millimolar, and that takes about a couple of minutes to achieve that concentration. So the generation is fairly fast. It happens in a cold finger at liquid nitrogen conditions, and you just irradiate with your UV lamp for those couple of minutes to get the concentrations that we need. But of course, this is for we use pyruvic acid in this case, but you need a precursor which is susceptible to excitation and can generate a stable free radical. So keto acids are good choices, but also other systems have been proposed and studied.
So we have one last question from Salvo Mamone. Great talk. How do you get contrast between hyperpolarized water and normal water? Is the background water saturated, or the signal of hyperpolarized water is so much higher than the background water?
A combination of both. We start the sequence in advance, and we have fairly high repetition rate, so it is suppressed, the background tissue, to a large extent. but the initial magnetization is 100-fold bigger than the normal magnetization. So with this fast acquisition, we are actually well above the normal signal. We would not be able to generate images with the same resolution and temperature and as fast. So it is orders of magnitude bigger.
Okay. Yeah, thank you very much again for the great talk, Jan. So for everyone, we have this informal session afterwards. So if you have more questions for Jan, I hope he can stick around with us for a few more minutes. And yeah, let's hand over to our next speaker.
Okay, sorry. Now it's my pleasure to introduce Christina Thiele. She started her academic career in 1998 in the group of Professor Jones at King's College in London, and with a diploma thesis related to natural product synthesis, so not NMR spectroscopy at the very beginning. Then she moved to Dortmund, did her PhD in organometallic chemistry, first context to the NMR spectroscopy. As far as I remember, it was one of the tin nuclei, 119 and 117. Her independent research, her habilitation started in the same year when she joined the group of Stefan Berger in Leipzig. Here she began to work with lyotropic liquid crystalline phases, especially with PBLG. And she started with the measurements of RDCs, residual dipolar couplings. After 3 years in 2005, he moved again, this time to my group at TU Darmstadt. There she stayed quite a while, as I recognized. It was till, yeah, really, it was till 2011. But as early as in 2010, she declined a call for a full professorship at the University of Bremen. Instead, 1 year later, she accepted the offer of TU Darmstadt to join the faculty as a full professor, which is also her current position here. Christina got a number of prizes and awards. I'd like to mention the Heinz Meyer-Leibniz Prize in 2010 and the RDC starting grant entitled RDC at Catalysis, right, Christina? RDC at Catalysis. And she's very active in several fields of NMR spectroscopy in the meantime, related to the applications of RDCs to solve stereochemical problems in small molecules. Moreover, she is engaged in the development of new chiral alignment media based on synthetic polypeptides, and she's very successful, I have to say, in cooperations with a number of organic chemistry groups being active in the field of asymmetric catalysis. Finally, I'd like to mention her activities in the development and application of new NMR techniques related to the, what shall I say, the in operandi observation of chemical reactions. Today, she will talk about something, yeah, more or less completely different, which is related to a new procedure to evaluate RDC data without application of these days more common structure validation and falsification approach. The title of her talk is De Novo Structure Determination of Organic Compounds from Multi-Alignment Datasets, Chances and Challenges. Please, Tina.
Thank you very much, Michael. And yeah, it's been really a long time since I'm here, and I still remember my first conference where I presented a poster on RDCs, and next to me was a poster from Christian Griesinger's group. And at that moment I thought, oh, either I can dig my grave now, or this is gonna be cool. As it turned out, life has turned out to be cool. So thank you very much, all of you, for having me in this seminar. I'll try to share my screen now. Let's see whether it works. It worked out when we tested it. Can you see the screen? Excellent. So as Michael has already pointed out, I'm a small molecule structure determination person. So it's a great honor to be talking in the emerging topics in biomolecular magnetic resonance. And when I got the invitation, I thought the project I need to show you is one that is well known in the biomolecular NMR field. And those of you who have been in this field will have seen these spheres with these cones that intersect at one point for approximately 20 years. And now the question is, why would this be also interesting to apply to organic compounds? And this is what I want to show you today. And also I want to point out what the challenges are and what the differences with respect to biomolecular compounds are. As I'm not a biomolecular and a mass spectroscopist, maybe I have some misconceptions concerning that, but I hope this is not the case. So the first thing we need to talk about is that if we talk about structure determination of organic compounds, what we usually talk about is compounds in natural abundance. So we do not have isotopic labels. And of course, as everybody, we first have to determine the connectivity. We will consider this a solved problem for the remainder of the talk, and we will talk about three-dimensional structures for now. And when we talk about three-dimensional structures, we talk about conformations and about relative configurations. So what you would be interested in, for example, is whether at this stereogenic center here and at this stereogenic center, whether the two residues that are here are pointing into the same direction, for example, both up, or whether they point into different direction as it's drawn here. So this means this is pointing upwards and this is pointing downwards. And this is one of the questions you might want to solve, so the determination of the relative configuration. And added to that, also the question of conformation, of course, turns up. So in this case, there are only two conformers, but if you have a normal 5-membered ring, you might have a number of envelope conformations that you might want to take into account. So just as a reminder, the more stereogenic centers you have, the more complex your problem becomes. So if you only have two stereogenic centers, you only have two relative configurations you want to discriminate. And the more stereogenic centers you have, the more different relative configurations you have and the more diastereoisomers you want to discriminate. Furthermore, if you then have rotable bonds, for example, like here, this makes your determination of configuration more complicated. So the more stereogenic centers you have and the more flexibility you have, the more complicated your problem gets. So you always need to determine the configuration of stereogenic centers and the conformation of your compound together. So this is an interlinked problem. How is this usually done when you talk about doing this with residual dipolar couplings? As Michael has already pointed out, what you need to do is you need to you put your compound into an anisotropic solution, for example, a liquid crystal, lyotropic liquid crystal, and then you can measure the total couplings. And if you compare this splitting you obtain here with the splitting you obtain in the isotropic case, then you get your dipolar couplings. So this is what we also do in the approach I'll be showing you today. However, the last step, the evaluation step, will be different. So what you usually do is you take a number of structural proposals, for example, the different diastereoisomers and the different conformers of the different diastereoisomers, and you fit your data to these structures, and then you have this verification or falsification of structures. Of course, the more complex your compound is, the more stereogenic centers you have, the more flexibility you have, the more complicated this approach gets. And there are some cases where you cannot discriminate the compounds anymore because you have too much flexibility, for example. So people have been working on approaches where you can actually use residual dipolar couplings as restraints or as pseudo forces in kind of structured determination programs, so that you do not have to put in a structure and do the fitting, but that you let the data refine your structure, basically. So the three papers that have done this very recently are cited here in the bottom. There is the progressive stereo locking by Gabriel Cornelesco, who has implemented this into Explorer NIH. Then there is the MDoc approach that Burkhard Louis has been talking about recently in this seminar series as well, and also the ConArch Plus by Stefan Immel and Michael Regedin that might also be worth reading. So this uses the distance geometry approach. But what I want to show you today is something completely different. because also in these approaches, you need to have kind of a starting structure, and you do this with one alignment medium. Which approach will be better in the end? We will see. You know, it's not, I do not say the approach I'm presenting today is better. I just show you it's an alternative, and maybe this will be better. Maybe the other approaches will be better. We will see. So the idea behind this is that if you have a residual dipolar coupling, this residual dipolar coupling describes basically a cone of vector orientations with respect to the magnetic field. And if you show this on such a sphere, then one alignment medium would be one of these lines. And if you have many different alignment media, then the different alignment media will lead to different orientations. So this cone will be tilted to some extent, and then you will get these lines that have different colors. And in the ideal case, these intersect at one, they have one joint cross-section, and this joint cross-section is then the vector orientation from the origin of the sphere to this cross-section. What you cannot see in this display is that there is a degenerate solution. So RDCs are invariant to inversion, so that at the back of the sphere you have a second intersection where these lines cross as well. So you can view this, if you do not know this method, you can view this as taking photos from different perspectives and then getting the three-dimensional image from that. So if you see, this has been published for the biomolecular NMR already 20 years ago. And from the point that I understood that this could be applied to organic compounds as well, I always wanted to do this, but I never found a coworker that actually wanted to try it, because this is a lot of programming approach, and furthermore, it's quite mathematical. So we first, of course, tried to do what Tolman wrote, and we failed. But in the end, now after several years, we managed, and I'll now show you where the challenges are in comparison to biomolecular compounds. So if you consider this this degeneracy of solutions, then you can imagine that if you want to discriminate those two compounds, that maybe if you have one conformation of this diastereoisomer and another conformation of that diastereoisomer, that you will not be able to discriminate them because of this degeneracy of solutions. I will show you one example here, where you can see these are diastereotopic protons. You can see one solution here and one solution there, and the difference in the conformation of the rest of the compound is not very large. In this special case, these are only two diastereotopic protons. So for just getting the configuration right, this wouldn't be such an issue. This would just be a wrong diastereotopic assignment. But this is an example where you can nicely see where the problem is. So when we started this project, I was curious to find out whether it's possible at all to determine relative configurations of organic compounds with this de novo approach. For this, several questions need to be answered. First, how can we deal with this inversion invariance, so with this degeneracy of solutions, and will this be a problem? Secondly, can we measure enough RDCs? From this problem and this depiction, you can already see that just one bond couplings will certainly not be enough. Then we need to induce many different orientations. So you need, for rigid compound in theory, you need 3 independent orientations, for flexible compounds 5. So can we induce enough independent orientations? And then the question always is, this is an iterative refinement procedure. How do I recognize in the end whether we have the correct configuration? So just because the optimization runs until the stock criteria are fulfilled, this doesn't necessarily mean that the configuration you get out in the end is correct. So these were the questions that we had when we started this project. So let's start with the first question. How can we deal with this inversion invariance in RDCs? Felix has, the student who, PhD student who has worked on this, has tried a number of things, and he was not very successful until he implemented the redundant internal coordinates. Redundant internal coordinates means that you have more restraints than you actually need. And what could this be? This could, for example, be dihedral angles, this could be bond length, but this could also be additional RDCs. For example, proton-proton RDCs. And you can see how this works out here in this depiction. So this inversion problem is seen here. And if you would have 3 couplings, for example, from these 3 protons to this one, then you can safely assign it. And you will be able to say that the red one will not fit. So you will be able to safely solve this invariance to inversion problem. So the trick is have more data than you need. And so how do you get more data? And I think a key to that actually really was the psychedelic experiment. So I remember when we talked about this in Pittsburgh at the ENC, and Davey had talked about the pulse sequence, and then he asked me, do you think we can apply this to residual dipolar couplings? I said, no, this will never work. We have this huge amount of couplings. We have these huge couplings in stereotopic protons. This will never work. And but I said, I'm happy to try it. Let's try it. And what you see here is a spectrum of this compound where this proton 4A was selected, and you can see the number of different total couplings that you see when you select 4A, and you see if you select 7S how many proton-proton dipolar couplings you get here, and also that you have a very large total coupling in the stereotopic proton pair. So I think this was the key. What else do we need? We need a number of different alignment media. So those of you who have followed that, we have synthesized a number of homopolypeptide-based media in the last 15 years, let's put it like this. And I want to point out especially the ones that have these blue circles now. These are thermoresponsive media. For example, for this copolymer of polyalphenyl aspartate with benzoyl aspartate, what we see is a very strong dependence of the quadrupolar splitting with temperature. And actually, these 2 points are the interesting points for the method, where you can see that if you measure at these 2 temperatures, which are before and after the helix reversal of the polymer, you can see that you get pretty different orientations. So this is what I think you need to know. Felix, when he actually recorded the data and when he checked for which alignment media can use, he used media only from our group. So he didn't even use the full potential that is there on the alignment media market. He just used ours because he had easy access to that. So what you'll be seeing now will be trajectories where we plot the chiral volume. And just for those of you who don't know what the chiral volume is, so if you have 3 vectors, you can span a parallel epipet which has a volume. And this volume has a sign, and this sign will be different if this vector points in that direction or if the vector points in that direction. So from the sign of the chiral volume, we can already say what configuration the stereogenic center is. So the 2 enantiomers, or the 2 different relative configurations at one stereogenic center, will have different chiral volumes. So you will see plots like this, where you'll see the chiral volume and the iteration steps, and you will see arrows here that indicate which chiral volume we would expect for the correct configuration. And you see, for example, this is a plot where we used the vector addition algorithm, and we started from the wrong configuration at this stereogenic center. And you see that very quickly this evolves into the correct relative configuration. So what did we start with? We started, of course, first to find out how many data do we need and how independent do the orientations need to be. So first we started with the simulated data. And when you simulate data, you can make your orientations as independent as you wish. And if you do this, you immediately see that only the CH RDCs, this would be 11 couplings, do not work out. But as soon as you add 6 proton RDCs, you already get the correct configuration. Then if you take orientations that are based on the media we have, so experimental orientations, then you see that the same is true. From 6 proton-proton RDCs onwards, you get the correct relative configuration. And the next plot is a surprise. Then we took media that were dependent, so that actually do not have or should not have enough information content, and also these give the correct relative configuration. The reason for this is because these are simulated data and they do not contain any error. So as soon as we add error, of course, these dependent data, they will fail. And this is actually what we see here. So if you take the same data, but you add Gaussian noise, then you see with the independent orientations, the same what we've seen before is true, that already from 6 RDCs onwards, the configuration is correct. If you take the experimental orientations, you see a surprise. Here, in this special scenario, even the 11 CH RDCs are enough to get the correct configuration, but I think this is by chance that this works out here. And if you have the dependent data, it doesn't matter how many couplings you add, this will not work out. And this is very reassuring. You see that here the trajectories are pretty busy. And then if you take a different algorithm, you can get these trajectories rather smooth. So you can use the vector addition algorithm and get this much more quickly. Why do we not always use the vector addition algorithm? Because if you have large scaffolds that you want to rearrange, then this vector addition algorithm doesn't work. Okay, so these were the first results. This was starting from the epimer at C3. This, I think, is very reassuring that it works, but the cool thing is what happens if we start from random coordinates. And what you will see now is we'll start from random coordinates, and what you'll be seeing here is the trajectory will build up, and here on the side you will see a histogram on how often the corresponding chiral volumes turn up. And hopefully this runs, yes. So what you see here is that first a kind of a reasonable scaffold evolves, and then some inversions take place, and you can see this also here in the trajectory, especially this center here inverts, and at some point this inversion stops, and then your structure remains stable. And here on the right-hand side, you see that the histograms show that the correct volume or correct chiral volume is obtained in most cases. For this one, you don't need this, but for the experimental data, you will need it. So this was all simulated data or calculated data. The question is now, can we also do this with experimental data? So what Felix did is Felix measured in 6 media, but as it turned out, only 3 of them were independent. And in total, he had 223 RDCs. However, as you know, if you try to measure in many different alignment media, you will not be able to measure all couplings in all media. So you will have this large RDC matrix, and you will have voids in this large RDC matrix. And then you have to deal with these voids. And the easiest way to deal with this is just remove couplings where you have voids, or remove media where you have many voids. But if you do this in an organic compound, then of course, there will not be much left over. So you will not have many couplings left over if you do this. We needed to do something different. And there are approaches in the literature described that you can, for example, take the iteration step before and back calculate how the RDCs should look like, or you can put in a weighting scheme and just weight these couplings very lowly or with very low weight. So what you see here now are the trajectories of the experimental data. You see the upper trajectory and this trajectory are starting from the C3 epimer, and these ones are the ones starting from the random coordinates. And you see different algorithms. One is this is the weighting algorithm, and this is the weighting algorithm, and these are the random the recalculation algorithms. What you see is you get the correct configuration out in all cases. This is the important information. Only in one case, the histogram is a bit screwed up, and this is because this inversion of C3 takes place at a very late stage. What you can see here is that we have 223 RDCs measured, and 23 of them are not available. Okay, so now the last question is, how do we recognize if the structure actually is correct? All these examples I've shown you, we knew what we want to have. So we knew what the curve volume should be. So how do you find out whether the structure is correct? First of all, what you need to check is whether the geometry you obtain is reasonable. Do you have a distorted tetrahedron or wrong bond length? Then your structure is not reasonable. And you can see one example here. This is out of one of the iterations with the experimental data, especially the one where we have removed all media or all couplings that do not have or that do have voids in the RDC matrix. And what you see here is that this bond is far too short. And then if you change a bit the stop criteria and the restraints in the optimization, then you get the correct configuration out. This happens because these couplings they restrain the bond length to that. So this is done on purpose, that we do not put back the correct bond length by force fields to be able to detect these distorted geometries. So this is the first thing. Look at your structure, whether this is reasonable. The second thing you will do is inspect the trajectory and the curve volume histograms and look whether something's strange there. And if something's strange there, then you can always start change the starting structure. Here we have only chosen two things, the C3 epimer and the random, but you can do many more. And you can adjust the settings. You can change the algorithm, change the stop criteria, etc., etc. So there are many things you can do. And if you change the algorithm and you get a different solution every time, then obviously you do not have enough data. So this is what you can learn, I think. So as time is passing on, and I do not want to take too much of your time, I'll stop at that point by saying, I think I've shown you that there is an alternative to this verification and falsification, that we can use this de novo approach to arrive at the correct relative configuration of organic compounds, even starting from random start structures. And the main issue was this inversion of stereogenic centers problem that was solved by redundant internal coordinates. Of course, this is not the end. This is just the start. So these were rigid compounds we have looked at so far and known compounds. Of course, the next step would be to look at unknown compounds with flexibility. And then we will see how far this approach takes us and whether we can also obtain local order parameters as have been obtained for biomolecules. This would be our gain or our goal. So I want to acknowledge people who did the work. So Felix Roth was the one that was actually crazy enough to do this project. He's the mastermind behind this program Titania. He's done all the programming, etc., and he was helped by Volta. This project is now taken over not from the programming side, but from the application side by Jan Rettig. So it's not that I didn't try to get money, but so far this has not been successful. So luckily I'm at a German university and I have some basic funding. Otherwise I wouldn't have been able to do this project. So so far this is all funded by TU Darmstadt. And as you've seen, It wouldn't have been possible if we didn't have the alignment media, and these are provided basically by the group. And so far we have only used our own media, but of course, as soon as we start using also other people's media, this will certainly be even more powerful. So I think we have another 5 to 10 years where we can investigate how this works out. And I hope you are as enthusiastic about this as I am. With this, I want to stop and I look forward to questions. I've seen Michael writing a lot, and I'm sure that also Christian and Markus will have questions.
Yeah, thank you very much. But although I wrote something down, it's really that's true. I would not say that I should. I have two comments, not questions, two comments. Okay. The first comment is there is a misunderstanding. CONARCH, which is the distance geometry-based protocol, can also use simultaneously an unrestricted number of alignment media. So this was wrong. There is only one. So you can use an unlimited number.
Can I directly answer? The thing is, you fit the data one by one. You take
no, we don't. No, we fit it simultaneously.
I think that's good for the informal discussion. Could you?
Yeah. Okay. And the next point. And the next point. Also, Titania has to know which atom sits on which other atom. So this means this means it's the very same starting point as with CONARCH. Yeah. And by the way, this is also a consequence that CONARCH can also use. We tried it for fun. Yeah, you can use arbitrary coordinates as well. So there's no difference concerning the knowledge about the things that go into the procedure. Okay. Other questions? I see quite a lot. There was the first question came from an anonymous observer. Why did you use the nuclear overhousing effect to determine the configuration of a small molecule? The NOSI spectroscopy is more easy and accurate for small molecules.
Well, I didn't have the time to go into all the details. Of course, the first step always is to use the classic NMR parameters. So when I try to determine a structure, the first step is always to look at J-couplings and NOEs. RDCs are only the solution if NOEs and J-couplings fail, which for flexible compounds happen quite often. So, but I'm perfectly with you. But if I had put in all the other slides describing what else you could do in organic structure determination, I wouldn't have finished, I think, in reasonable time.
There's another question from Stefan Immel. Thanks for the interesting talk. First, just a comment on that stated distance geometry can. Okay, this is related to this multi-alignment thing. And later on, he says, okay, then he obviously recognized that I criticized this. And the next was, Tina, this is wrong. So Stefan, please, or let me please comment on this multi-alignment thing. Is he able to comment from outside?
Yes. But I mean, there was this question: how much data will be needed for Titania?
Yeah. How much data is needed on the one hand, and the other thing was this multi-alignment data treatment.
I mean, let's first go through the questions,
yeah.
And then we go to the informal, and then we can invite more people also to the panel.
Yeah. But he cannot answer now, or how is it?
No.
The idea was that we do this discussion in the informal part, and you now read all the other questions first.
Okay, then I see wonderful talk. Just curious, wait a moment. Will conformational dynamics of small molecules also be characterized using RDCs?
I hope so. We will see.
Also, I see that different solvents have been used for obtaining alignment. How do you envisage solvent effects to conformational dynamics of such species due to the difference in the microviscosity?
So far, what I can say is we have investigated several flexible compounds, and we've never seen an effect of the liquid crystal on the conformation. But of course, we do not check this every single time. What I can say, in theory you can do is you can try to measure your compound in a solid state rotor at the magic angle, assuming that your liquid crystal is still alive. And then you can measure the isotropic scalar couplings. And if these are the same, you can assume that there's no influence. Furthermore, what we see is that usually the chemical shifts change only by constant values. And the chemical shifts do not change differently for different positions. And in organic compounds, these effects on conformation on the chemical shift are sometimes pretty large. So usually, I wouldn't say we can always exclude it, but so far we haven't seen the issue yet. But this approach actually will allow us to assess this to some extent, hopefully.
And Armando is asking just one question. How large were the intertensor angles between your different phases? So the question about the linear independence of the media.
Yeah, so I do not know them all by heart. What I can say is that looking at all the intertensor angles makes it quite complicated. How we check linear dependence or linear independence is by the Seconda approach. This makes it much easier. And then you look at how much of these eigenvalues contribute to the cumulative sum basically. And then you see if, let's say, one medium only contributes 0.1%, then this is certainly linearly dependent. But if this contributes like 20%, then this is fine. We do have all the intertensor angles in the supporting information, but I do not know them by heart. But the ones we have chosen to be linearly dependent are things like the two enantiomers in PBLG. So there we know that the intertensor angle is only like 7 degrees. And the ones that are very different sometimes are 30 degrees or so.
So Claire Dixon is asking, does psychedelic require that you are able to select one of the protons?
Yes, I think so. You can also select overlapping ones, but then you need to be sure that they are not in the same spin system. So as long as they are in the same spin system, this is a problem. But I could envision that you could incorporate this spatial selection that the Morris group incorporated into the NOSI experiment, so the gemstone experiment, that you can also combine this, but I'm not too sure. One needs to think about this. But so far, this has been okay-ish.
Lukas Kalschnee. For the 1H RDCs, do you have to make corrections to the apparent line splittings in psychedelic to account for strong coupling effects to get the correct dipolar coupling?
As soon as you have strong coupling, I would keep my fingers off, to be honest. But we haven't seen, in the examples we have looked at, we haven't seen any problems so far. So we haven't seen any problems so far yet. But of course, if you see that there's strong coupling, then you need to take measures or just move the roof, leave them out. That's what I would do.
Okay, another anonymous just ask, can't you just crystallize these small molecules? Okay, if this would be possible, then of course you can.
So, maybe I didn't make this clear. So this is a method that you would apply only if other methods fail, of course. So if I can crystallize a compound to determine the relative configuration, I will always crystallize it. If it doesn't crystallize, then I would always first try J couplings and NOEs. And if this fails, then I would try RDCs. And then, first of all, I would try to do the best fit approach. But if I cannot discriminate it, then I would go for this method. So this is not the first thing I would try. But as soon if you develop a method, you need to develop it on a compound that you know. And this is what we did here. And yes, the crystal structure of that compound is known.
Okay.
So I would say that we slowly proceed to the unofficial part. So thank you again, both speakers, for exciting presentations, all the chairs, of course, for doing all the work. Thank you, Michael.